A continuación, el trabajo de Roadmap to Autonomous Remote Monitoring of Offshore Facility, Wind Resident Drone, and Emission Sensing Technologies. Wanjoo Choi, welcome to Wanjoo, the Equinor.
Thank you. Hi, I'm Wanjoo Choi with Equinor. Good morning. I'm sorry that I do not speak Spanish. I do hope to learn Spanish soon. I'm part of the Shale Oil and Gas Research and Technology Group in the U.S., responsible for R&D functions for our global onshore operations. My presentation today is about our work on emission sensing technology development as part of our efforts to lower greenhouse gas emissions. I'll talk about the background, methodologies, and results and future plans. So before we dig into details of my work, as the background, I'd like to give you a brief introduction to Equinor. As a broad energy company in Equinor, our business is not limited to oil and gas, but includes renewables, CCUS, carbon capture, utilization and storage, and hydrogen. In Equinor, we care about the people, the society, and the environment where we belong, as our purpose is to turn natural resources into energy for people and progress for our society. With this in mind, shaping the future of energy production with always safe, high value, and low carbon operations is our vision. We are very much aware of the global climate changes and greenhouse emissions. We are working closely with our partners and stakeholders to make energy production less carbon intensive, and climate is embedded in our decision-making processes. On Equinor operated facilities, our corporate goal is to reach carbon neutral globally by 2030. This means the carbon intensity will below 8 kilograms per barrel of oil by 2025 and zero or near zero flaring and methane emissions by 2030. As you can see the graph, Equinor is already far below the average industry CO2 intensity, as you can see, and our trying to lower this CO2 intensity further down. And the flaring intensity is far lower than IAPG average, but also we want to lower it down further below. So let's talk about methane sense technologies. We cannot eliminate emissions unless we know exactly where, why, and how much those emissions are happening from our production facilities. Since 2013, Equinor US has been taking facility-wide emissions survey using forward-looking infrared cameras or flare cameras, and have prudently fixed many malfunctioning equipment from our legacy well paths. The survey results indicated that majority of emissions happen from a small subset of sources, mostly resulting from unexpected malfunctioning equipment. These non-routine fugitive emissions is a problem to us. So we need to fix it. As you can see from this video, I'm not sure if you can see the video. Yeah, it's not playing, but this is fugitive emission coming from the malfunctioning emergency pressure relief valve on top of tank battery. This is not intended, obviously. We want to find it and fix it as soon as possible. So there are concerns in health and safety to our personnel and neighboring community. And also this kind of loss of product or loss of revenue to fugitive emissions is a concern to our interest holders as well. And this is non-compliant. So timely identification of this kind of leaks or emissions is very important, but it's a big challenge. Because it is very difficult to identify these equipment malfunctions, and efforts to identify those malfunctions are very labor intensive. So ideally, we want to have sensors on location so that they can detect and notify those problems as soon as possible so that we can dispatch people for quick fix and investigation for the investigation. So we want to develop new generation methane sensors for the cost-effective carbon management. In 2013, there have not been good methane sensors available in the market. So we kind of spearheaded the development of methane sensors by working with academia, government agencies, and other industry partners. So development of high precision, low maintenance methane sensors that can give us leak quantification and leak localization and real-time notification has been our purpose. So I'm giving you the result from 2 methane sensors that we have chosen and tested and implemented. So since 2017, we have implemented methane sensors actively in our well paths. And sensor A and sensor B, 2 are the examples. I could not give the names because of IAPG regulation not to disclose the brand names there because they have been commercialized already. So I'm just marking them in terms of sensor A and sensor B. So both are methane sensors, and sensor A is a stationary sensor unit. And sensor B is a drone mount sensor unit. So you can see sensor B has the mobility. And both sensors have similar technologies, basically laser-based technology, laser spectroscopy. This is tunable diode laser detection spectroscopy. The other one is open path laser spectroscopy. But the sensitivity is slightly different. Sensor B has been a little higher in sensitivity. And the reporting frequency is a little higher on sensor B. It's interesting because it'll be smaller, but it has high frequency and high accuracy. Sensor A has been implemented in our well pad in South Texas, and sensor B has been implemented in our South Texas well pad and also North Texas well pads. So this is the photograph of sensor A implemented on our South Texas well pad. This is the unit here. It has sensor block behind this solar panel, and we have battery equipment here. And obviously, the equipment in front of this sensor is the valve control equipment. And this is well pad. This is where the sensor has been located. So this is northeast part of the well pad. And you can see we have tank batteries and well heads. And this is compressor and separators here and control valves here. This is a sensor B, which is drone mount sensor. As you can see, our pilot is flying the drone, flying around the well pad. And this is the actual footprint of the drone flying inside the well pad to detect any leaky equipment there. And this is an example of actual detection of leaks, and the flux has been overlaid on top of the map. With sensor B, because it's a drone mount sensor, you can do more things. We have developed protocols for 2 different purposes. One is find and fix protocol, so that the drone can find or sniff the source and trace the source all the way to the equipment and let the LDOR team, leak detection and repair team, know the problem, then they would go and fix. So that's protocol A. And protocol B is emission footprint. So we wanted to know how much methane emission is happening in the well pad. So we would do a perimeter survey. Basically, we would do the survey upwind of the well pad and downwind of the well pad so that we can understand what's coming in and what's coming out. That will give us flux information of the well pad. So this is the result of sensor A. So basically, it gave us high frequency methane data and the directions where the methane plume is coming from. So this is the average methane levels and the direction. So methane is coming from obviously south-southwest direction, which is the dominant direction, and the methane concentration is between 2 and 4, like that in average. But the wind is coming from southeast. Basically, this difference of about 45 degrees, and the prevalent wind speed is about between 2 and 4. This pink color here, and sometimes it can be a little stronger, but the average is between 2 and 4 meter per second, and it's coming from southeast. And sense A was kind of difficult to use because of the location and the limitation of having one sensor on the well pad. Obviously, we have equipment widespread in the well pad, but from the sensor location, they are located in the similar direction, very narrow angle. Basically, we have some valves here, compressors, tank batteries, and flares on the west. But when it gives the angle and the quantity, we could not really pinpoint the exact source. That has been the problem. As you can see, the azimuth are not very far different, even though the distance from the sensor is kind of widespread. So wind direction and actual plume directions have been different. That has been a problematic to me. So obviously there's a strength. Sensor A gave us high sensitivity data, and it was able to detect as low as 0.96 ppmb, which is below 1 ppm. Probably that has been the baseline of this area when there's no contamination around in the atmosphere, which is kind of lower than the average, which is about 1.6 worldwide. And it gave us high frequency reporting, like 1 hertz, which means 1 data point per second. And it has been very durable and didn't require any maintenance for the 2-year period. But again, the weakness has been the poor localization because it depends on the wind strength and direction. And also it requires weather data. We had anemometer, which detects the wind speed and direction. It failed, one of the cups failed, and it gave us about 14% of loss of the wind data. So that has been the weakness. So even though we got readings from all directions, because of the narrow angle of the equipment, we probably were able to guess which direction the emission is coming from, but we could not understand the readings coming from different directions. That has been the issue. So recommendation would be that we need at least 4 sensors on the well path so that we can triangulate the information better, and probably better working anemometer as well. So sensor B is a drone-based sensor, and this is the example of data that we captured in July 2018. So it gave us the elevation data, while the fixed sensor gave us only the concentration data. So the elevation, it was between 0 and 72 meters above ground level, and concentration, the average concentration has been between around 1.6 and 3.7, and the average being around 1.97, like that. So the advantage we were able to see the advantage of having this sensor immediately because it has the mobility. It was able to approach to each equipment and was able to calculate the flux coming from each equipment at the well pad. So this is the result of about 34 different well pads, and all the non-emitting equipment has been eliminated here. But this is the kind of baseline of those emitting equipment here. So we see some high flares, high flux coming from heater, treater, and flare stack. Obviously, they mean there's an incomplete combustion of fuel gas happening. And some high values were reported from separator and valve house, like that. but mostly the wellhead showed high integrity, showing not much flux. So we can see the advantages having this kind of drone mount sensor because it can sense actively by sniffing the plume, and in its mobility was able to help us trace the plume all the way down to the source. And because it was able to create 2D flux plane or 3D cube for understanding the flux of the equipment, not only the equipment, but also the well pad itself. It gave us very good calculation of the flux coming out of the equipment or the pad level. But there are weaknesses as well because there are some regulations that we have to comply with. There's a Part 107 FAA regulation, so we can fly drones only under good weather and only 3 times during the daytime, and only within the visual line of sight. And one pilot can fly only one drone at a time. However, we was able to see the potentials. Like we can capture more data beyond the methane data when we integrate other sensors, because we can capture high-value data from the sensors, like visual camera. With visual camera, you can get situational awareness improvement there. And with repeated surveys, you can compare the differences so they can capture anomalies. So when there's anomalous information, you will be able to do further investigation and take appropriate action. And thermal infrared camera will be a great sensor so that you can detect anomalous heat objects, because there are some heating situations going on all the time. We have flare stack, and also we have separators, and we want to know if there's an anomalous heating situation going on. There can be fires in the well path, so we want to know them as soon as possible. So thermal infrared will be a great help. So this kind of integration will give us great potential of improving our safety and HSE in general. And automation and digitalization of this equipment and processes will give us a chance to implement managed by exception concept, because in that way you don't have to send your pumper every day. When you can send people there only when there's actual problem. And this kind of technology can be implemented not only to onshore but also to offshore facilities. So, so what is the pathway to the future? Actually, this is what we are currently working on. So we are working on the integrated sensor payload development. We are integrating the methane sensor and visual camera and TIR sensor together at this time. And in the future, we do hope that we can integrate OGI sensor as well, optical gas imaging sensor. But because of the size of the sensor at this time, they cannot be easily integrated with other sensors. So that'll be coming next, but we are working on this one. So sensor integration. And the drone needs to support long-range aviation. Right now, because of the battery limitations, we can fly only up to 25 minutes like that. They are now improving. They can fly up to 1 hour, very close to 1 hour. So we are working on that one so that we can identify long-range drone platforms. And the housing, which can be protective housing, which will allow drones to stay on site and fly kind of autonomous fashion whenever it is necessary or whenever it is scheduled. It'll work as a ground control station, and also it'll charge and process data coming from the drone. And also we need BBLOS infrastructure beyond visual line of sight infrastructure. You know, we can make it ourselves, but we need to get permission from FAA. Actually, in case of North Dakota, they are helping the oil and gas industry with the infrastructure. Right now, those efforts are going on, and FAA is very supportive on that one. So here's our little kind of animation, what the future will be like. So drone will stay on location and fly autonomous fashion. and it'll collect information from.
Sorry, Wanjoo?
Yep.
5 minutes.
Yep.
5 minutes.
Thank you. Autonomous fashion, and it'll collect information from the well path, and it'll be able to label whether it is green or yellow or red. And it'll cover not only the well path, but also pipeline right of ways, and detect and quantify and notify our operators. So that is my presentation. If you have any questions, please let me know. I'd love to answer these questions.
Thank you, Wanjoo. A question. Could you share any release SPE, paper number, or any other publication ID about this test?
We have not published papers on SPE, but with this presentation, I submitted my 5-page paper, which actually summarizes, in a scientific way, what we have done very well. So hopefully, IAPG can share that information with everyone.
Okay, Wanjoo, very interesting, and actually your presentation, and thank you.
Thank you.
Bye-bye.